All right, let's take it away. Welcome, everybody, to Genetics in Action, Evolutionary Algorithms. This is, as I was mentioning before the recording, the first time I've delivered this talk in literally years, but it's more of an academic topic, so there's been a little bit of movement in the field, and I may touch on some of this, but the level at which I'm discussing things fundamentally hasn't shifted that much, so we're still good to go. Who's we? Well, I'm me. My name's Kevin Feasel. I'm a data platform MVP out of Durham, North Carolina. By day, I'm a data scientist at a company that builds large ships, and sometimes I also do a bit of consulting. But I've got a blog called Curated SQL. The idea of Curated SQL is every day I try to find and link to 5 to 10 interesting posts on topics all across the data platform space. So it's curatedsql.com. What I want to do in this talk is stare straight ahead, but I'm going to have to look this way because that's where my slides are. But we're going to get an introduction to this notion of evolutionary algorithms. I'll explain some of the intuition behind how they work, and then we'll focus in on a trio of specific concepts: genetic algorithms, genetic programming, and evolutionary trees. So we're going to understand a little bit about how does this tie to evolution as a biological concept, some of the metaphor and how it applies in programming. We're going to look at the types of problems that evolutionary algorithms tend to be really good at. And then we're going to solve some of these sorts of problems, understanding what the outcomes look like and how we can possibly optimize our results. We'll look at a variety of scenarios. So this one will be around maximizing a stock portfolio, and even things like trying to solve equations where we have data, but we don't know the underlying formula, and attempting to estimate out an approximately good solution. That's the idea. If there are any questions at all through this, please do feel free to add a message in chat. Chat will be right in front of me on this screen. Or if you want to raise your hand. Otherwise, I'm going to go through the slides. We'll go through plenty of demos, and I'll give you links to where you can grab the code, the slide, and additional resources at the end. So let's start off by asking the question, well, what exactly are evolutionary algorithms? And these are a set of algorithms that are great at solving a particular collection of cases. Cases where we have an extremely large search space, something that a human couldn't easily solve, something that a brute force algorithm couldn't easily solve. But we have a way to score our answers. So I may not know exactly what this formula looks like or how to optimize a collection of items, but I do know if that is a good answer or a bad answer. And this complex solution, obviously, if we can do it by hand, we're not going to use a more expensive algorithm computationally to try to solve this. So there's a minimum threshold for where it makes sense. But we do believe that there is an answer. So in particular, the computer science term that pops up a lot with where genetic algorithms tend to work is NP-hard problems. These are problems where there is a solution. They're not impossible, but there's not necessarily an optimal single solution or a single algorithm that will automatically give you the best solution. And this is where evolutionary algorithms really rule the roost. Okay, I mentioned NP-hard problems. What are some of these types of problems? Well, in the optimization space, if I'm trying to minimize or maximize something, I want to maximize the number of items that I can fit on a single truck. I want to minimize the cost of delivery. Maybe I'm doing circuit layout or antenna design. That was a classic example that, if I remember right, NASA was doing, where they would use genetic algorithms to design antennae that were more efficient, solving things like the traveling salesman problem or the knapsack problem. In machine learning, we have some integration with neural networks, building weights for neural networks and also keeping neural networks on track. I will talk a little bit about genetic algorithms and evolutionary programming vis-a-vis neural networks at the end of the talk, But I do want to note this is not a neural network talk. We're not going to get really into that particular topic. What we do see is in other practical scenarios in economics, we may look at portfolio maximization or trying to solve game theoretic problems. In the ecological space, think about host and parasite coevolution. So how is it that a parasite may survive without killing all of the hosts and thereby dooming itself? So we have this whole notion of min-maxing, and genetic algorithms and other evolutionary algorithms can drive us in that right direction. The common term that we'll hear quite often in computer science is a hill climbing problem. And the whole idea of it, I have just a very simplistic image, and I'm going to switch to blue. Let us suppose that we want to pick on this axis the maximum point. We want to get up to here. But the problem is, you and I can see the picture, but let's say we don't know what the picture is. All we know is that we have some range of values, and we get to pick a value. So maybe I'll pick like that value right here. And then I'm not sure if that is the best value. So there are algorithms that will help us, like such as gradient descent, that will say, hey, go look a little bit over this way and see how you're doing. Oh, you're worse. Okay, well, try on the other side. Oh, look, it got a little bit better. Well, let's keep going in the direction where it's getting better until we reach a peak. And then we say we have at least reached a local maximum. But the problem is that type of approach may get us stuck at a local but not a global maximum. So we may not have an optimal solution. Now, obviously, it all depends on where you are in here. Like if I started us off right here, yeah, we would be able to get easily to the maximum. If I start us over here, we could technically still get to the maximum if we search every single possible point. But if it takes some amount of time or compute effort that is not insignificant, then we may not want to test every single possible point of this range, or it may not be physically possible for us to test every point. And that's where we can run into an issue with this hill climbing type of approach, where we can get stuck at a point where it's good. Maybe it's good enough, but it's not the best. All right. So that's the kind of problem that we're really digging in on. And there are a set of heuristics that help us define what makes for a great solution. Obviously, we want it to be correct. We want to get the correct result. We want to get this correct result every time we run the program. We want to make sure that it's justifiable, that our inputs we can explain as giving us these outputs. We can at least have some understanding of it. And we don't want the solution, like coming up with a solution, to be based on random chance. I don't want to flip a coin and if it's heads, I'll get a solution. If it's tails, I'll fail to get a solution. We want something where every time I run this program, I get a solution that is correct, that is understandable. And in an ideal world, our algorithm should be step by step and very orderly. It should be a logical process that a human can follow and understand. And ideally, all other things equal, ceteris paribus, simpler is better. So we want a parsimonious solution. And we want one that's decisive. Once I have an answer, I have the answer. I don't have to go back and look at it again tomorrow and see, well, has the answer changed? These are what we would consider to be indicators of this is a good solution. And evolutionary algorithms guarantee none of those. In fact, we kind of go the opposite direction because there are a series of limitations with them, such as I can't guarantee that you'll ever get a solution. If you run this thing, it might not give you a valid solution. It might not work well in terms of good performance or finishing in a reasonable amount of time. There's no guarantee of it. Every time you run the program, you're liable to get different answers. And this isn't just based on your pseudo-random seed. This is essentially baked into the design of how these processes work. it's hard to tell when to stop. It's hard to tell because we probably don't have a perfect answer. So, at what point are we at a good enough state? Or are we not going to get better at the very least? And even with all of this, we still might get stuck at a local minimum or a local maximum. So, we're not guaranteed to hit that global min or max. And our solutions, as I'll show just a little bit, they tend not to be parsimonious. There tends to be a simple, clever answer that an evolutionary algorithm may get, but probably won't. However, why am I here? Because they still get the job done. These are workmanlike algorithms where there's no guarantee of success, but it sure works a lot of the time. Okay, that's the primer on evolutionary algorithms as a whole idea. Now, we've got to go back to high school biology. We're going to talk just a little bit about genetics, just so that we're kind of on the same page when it comes to terminology. The implementations of algorithms don't rely on you having a deep knowledge of biology, but it does help understand how the algorithms work. So these evolutionary algorithms, they're modeled after a simplified form of the biological process of evolution. And here I've got the example of Darwin's finches, of how on different islands, finches develop different beak structures to handle different foods. Well, each organism has a set of chromosomes, and the purpose of a chromosome is to carry genes. In an evolutionary algorithm, you can think of an organism as a candidate solution. So our concept of the organism is one of our agents in the solution set. And specifically for genetic algorithms, we have one chromosome. So we have one set of genes. A gene in real life, these make up DNA sequences that are called genotypes. And the genes have various alternative forms, alleles. So you could think of this as determining eye color, hair color, characteristics like that. Genotypes are our possible genetic structures. And so if I have two alleles, if I have two possible outcomes for each of 32 genes, we've got 4 billion genotypes that are available to us. Now think of the search space there. Think of having to search across 4.2 billion genotypes to try to find what is the optimal set in terms of solving some particular problem. And you can start to see where the complexity comes in, that if it takes a while to determine, is this a valid answer, is this a good answer, doing this 4 billion times going to require a lot of hardware. On the physical characteristics side, so phenotypes, these are the observable physical characteristics. In other words, our genotypes will drive the physical characteristics, the phenotypes. So coloration, height, size, eye color I mentioned. But there's not really a one-to-one correspondence. So it's not like this genotype controls eye color. It is more of a complex intermixing of many different genotypes. So the phenotype will depend on a combination of alleles. And what that tells us is, tying into the computer science part of evolutionary algorithms, it's if I give you a set of inputs, I may not be able to break that set of inputs cleanly out and say, elements 1, 2, and 7 combine to form this part of the result. And so I can change 1, 2, and 7, and that will cleanly affect one part of the result without affecting everything else. Essentially, this is typically a much more complex problem and a more complex solution set. So when even one allele is missing, you can get a significant difference. And close counts in hand shoes and horse grenades, whatever, horseshoes and hand grenades, but it doesn't count with genetics. Now, we also have this notion of a niche, or a niche if you're French. So this is a set of features that certain phenotypes might be able to exploit. And this particular is, in particular, is a set of environments within Europe. And so you have everything from arid desert in central Turkey going up into polar climes. And basically, animals that may thrive in something that's more of a temperate climate may not work so well, say, in northern Sweden. So we have to think about what is the environment in which we're trying to solve the problem. And tying this in to our scenario, maybe if we think about economics, the portfolio theory example, well, I may have certain characteristics, like I want something that is less volatile. And so I may focus on a less volatile set of stocks if my environment tends to be very volatile or is extremely low growth. So I may be focused on a particular type of stock, and that may be better than in a scenario where we have less overall volatility and higher growth on the whole. In that case, I'm looking more for value than I am for risk reduction. And so the environment can affect the best solution. The environment will help drive what actually is the solution to our specific problem. All right, all of that stuff, just think of this metaphorically, similar to, we talk about neural networks, you'll have pictures of brains, and you'll talk about axons and dendrites and the like, and then you get into the actual programming and you say, well, what represents an axon? It's not a perfect metaphor. In the genetic space, it's not a perfect metaphor either, but it's a motivating metaphor. So I want to talk about first genetic algorithms. This was the progenitor of, I would argue, is the progenitor of this field. It was a fantastic algorithm and popularized by John Holland's book entitled Adaptation in Natural and Artificial Systems. A really good book. I wish I had a physical copy here that I could hold up. And now I wish I got my prop for later on, but that's okay. So I want to show you, before we get any further, before we get into the concepts and the structures, our first demo. So that way I can say we had a demo within the first, 15 minutes. All right. I have a notebook here. This is in R. All of my examples today will be in R. You could do this in Python, and some of this you could do in other languages, but R and Python will be the two major players. The library of choice is the GA library. And by the way, if you would like me to bump up the font size, just let me know. But I'm pulling in this GA library and saying, I have a function. So my function, I am defining this, and it will be the quantity x squared plus x, and I'm going to multiply by the cosine of x. And I'll show you a range from -10 to +10. And I want to show 1,000 points along that range. So draw it as a curve. And what we get is something that looks like this. So in other words, this is, I know what the solution is. I know what the actual mathematical function is, and I know what the maximum is for this range. However, I'm going to throw the problem at a computer that does not know what is the function. It won't know the underlying characteristics. It won't know what the maximum is, but I'm going to ask it, find me the maximum. And we can do that by using the GA function that is part of this GA library. I'm going to look in real values. So in other words, this is a decimal value. My fitness function will be derived by this. It doesn't know exactly that the formula is x squared plus x quantity times the cosine of x. What it knows is that if it passes in a value of x, it's going to get back something. Our fitness function is essentially telling us how closely do we match to the environment? How well are we doing? Our lower will be -10. Our upper is +10. So I'm going to make sure that we stay on this range. And if I run this, it won't take too long. Looks like it's already done. So I can hit the summary, we can see that my population size was 50. So I had 50, think of this as 50 animals, 50 candidate solutions. If you want to, so I would go with animals if you want to think of this like a nature case, and 100 generations. So we've got these 50 animals. We're going to have them exist. They're going to make babies. They're going to die off. Babies will take over, and so on and on and on, 100 separate times. What we end up with is a fitness function value of 47.70 at x equals 6.56. And if I plot the convergence of this, what we see is my best score, my median score, my mean score. The first few generations, it's actually kind of not great. The best scores, even early on, the best scores actually do a good job in this scenario, in this run through. We can see that they come close to maximizing, but it took maybe 15 generations for us to get rid of most of the bad solutions. And so now, after 15 or so generations, we have our normal solution is really good, but there are downward spikes. So occasionally we have a case where a whole bunch of bad solutions just pop in. And we'll talk about what can cause that, what does cause it, and why, on the whole, it's actually a good thing. But we were able to see a conversion. And if I point out that curve and I see what my maximum value was, yeah, we can see we got the max. And so we were able to do it. 50 elements of the population, 100 generations. So we actually calculated 5,000 separate data points to find this. 5,000 is a lot of data points. We could always have possibly lowered the number of generations, lowered the number of elements of the population per generation. But wanted to give you an idea of kind of how some of the mechanics of this work in code before we dove into the mechanics of how the algorithm works, which I'll do next. Go for it, Raymond.
I think you can learn how to unmute myself. So this sounds a whole lot like a Monte Carlo simulation. What's the difference between GA and what I would know as a Monte Carlo?
All right, great question. So it does, in some cases, sound a bit like Monte Carlo, and I think as I show the process a little bit, you'll see some of the difference. But Monte Carlo simulation is, I would say, it's a little more structured than what we would necessarily have in a evolutionary algorithm. We're expecting parameters with certain bounds and certain levels of variance. And so we're trying to simulate some number of times, 10,000, 20,000, 30,000 times, and try to understand, well, what happens if this element gets tweaked or this way or that way? And what does the broader range look like? So we can use that to solve similar types of problems. But I personally envision Monte Carlo as more like top down. I'm explaining the nature of the space and the possibilities that you're allowed to vary, versus the more bottom up of, I'm going to give you the parameters that you're allowed to organize around and allow that organization to happen. So that's a little bit wishy-washy of an answer, but hopefully that tides you over until we explain the nature of how a genetic algorithm works. All right. Tying back to our genetics terms, our organism, every organism in this scenario is a candidate solution. So I mentioned that I had a population of 50 organisms. So I had 50 possible solutions. Now, the solution array is our chromosome. Our solution array is a set of input points that combine to derive either what the formula is or what actions we're supposed to take or the quantities of different elements that we want to have. And that forms our chromosome. Every chromosome has a set of genes. Each gene is one element of the solution array. So if my solution array is an array of 16 numbers, we would have 16 genes. So the locus is the position. That is the 9th element of the array. That is the 9th gene, the locus of 9. The allele is the specific value. If it can be a 0 or a 1, we would have 2 alleles. We have where that 9th element is either a 0 or a 1. If it's a floating point number, we may have a much larger number of alleles. And our niche is the fitness function. That is, how can we, what is the thing we want to maximize? What is the thing that we want to score against? And this is how our metaphor is kind of playing in. Now, when it comes to genetic algorithms, most of the time what we're dealing with is an array of binaries. And I have a couple of chromosomes, a couple examples here of my elements of the population. So red and blue. And we have our chromosome that contains, in this case, 8 genes for each. You can see that sometimes they'll match up, sometimes they'll differ. And that's exactly what we want, because we're going to build a population of these things. We're going to have some of them, and our starting point is just randomly throw in zeros and ones. I don't know how to solve this problem, but I need to start somewhere. A little bit of a Bayesian style of starting point. We don't necessarily have a lot of information. I just know the shape of the solution in terms of what I'm allowed to input, and let's just start inputting things and seeing where we go. Now, after we build the population, we have to score the fitness. And so our chromosomes are the inputs to that fitness function, and we get back some value. And this is critical here because that value is what we use to score how good a candidate solution is versus other candidate solutions. So we need to have a comparable value. Basically, it needs to be a number, and we can say this number is bigger than that number. So now each chromosome has its own score. We can compare versus other chromosomes, and we can even say, hey, if I want to build out my next generation, I want to take some of the best characteristics from my existing population, survival of the fittest. And the way that we do that specifically in genetic algorithms is we take the summarization of all of the chromosomes in our population, all of those organisms, and we sum up the values of their fitness functions. So in this case, we had a 170, a 128, a 116, and a 94. That adds up to 508. Then we say, okay, of the total fitness of the population, this red fellow was worth 33.5% of the total score. This blue was worth 25%, and so on. And then we start rolling the dice and say, okay, generate random numbers. We need to generate, let's say our population is 50. We need to generate 50 new results based on these probabilities. So if I generate, there's a 33% chance that I'm going to pull a red, a 25% chance of a blue, 22 of a green, 18 of a yellow. Now, these lower fitness results, we can still get them. There is still a 22% chance that I'm going to pull a green. So in this case, if I just pull 2 out of a hat, what I'm indicating here is there's no guarantee it's going to be 2 reds or a red and a blue. It could be 2 reds. It could be 2 greens. It could be 2 yellows. The probability of it being 2 yellows is the lowest of all the possible set, but it is still possible. Then we take those results and we say, okay, we're going to perform crossover. We're going to essentially mate the good results. And the way this works in a genetic algorithm, a classic genetic algorithm is I have, I pushed the wrong button. I have a mating pair. I have a red and I have a green, and I'm going to say we have the same number of genes. So the chromosome has to be the same size and shape. And I will, again, roll the dice and see at what point, at what locus do I start crossover and at what locus do I end crossover. And in this case, we're going to start at the third element and end at the fifth. And so what I'll generate is a new result that is the combination of its parents. So I have the new generation. So our fitness first was basically, think of that as survival. And then we have the mating period, and we generate out these new chromosomes that are maybe different from what we've seen before. So this is crossover. This is one of the two ways in which we get evolution in this algorithm. The other way that we do it is with mutation. Mutation is, with some probability, we're going to, again, roll the dice and say, I'm changing one of these. I'm changing this from a 0 to a 1. The parents, maybe they both had 0. But due to a mutation, we had a random change. This is how we introduce randomness, some variety into a stagnant population. This is how we keep from, hopefully keep from landing at a local maximum. And usually mutation is very low probability. So 1/10,000th of a percent to 1/100th of from like 100th of a percent to a 1%. Usually we don't want to go above about 1%, 2% for mutation, because then it starts getting too scattered, too random. We have a difficult time focusing in on a solution. But we also want it to be above 0 because we don't want to get locked in on a local maximum and be incapable of bouncing off of it. So that's the general idea. We have crossover and we have mutation, and those are our two mechanisms of modifying prior generations to create new generations, and we repeat this process for however many generations we need to go through. And so that's our new organism. We're going to score it and repeat. That's the high-level understanding. And where genetic algorithms make sense are in specific search problems. Got a couple of them on the list here. The knapsack problem, we have portfolio selection, we have the traveling salesman problem, and we have the Holyfield problem. Now, the Holyfield problem comes from Vander Holyfield's Real Deal Boxing. And if you're of a certain age and had a Sega Genesis, you may remember Vander Holyfield's Real Deal Boxing for the Genesis. The idea of the game was you'd been a boxer, and you would have different options you could choose. So each one of these provided you with some benefits, but you only got a limited number of options to choose from. So how do you make the right choices given what is available and what are the stakes? And we're going to solve that problem, which is demo 2. This is the Holyfield problem. Now, this is actually just a variant of the knapsack problem, but I figured, I remember the game. I had fun with the game and kind of enjoyed it. By the way, if you do want to see, in the repo, I do also have HTML results. So you can see the notebook is more like a classic notebook. So you're welcome to check those out. But we're going to focus here mostly on the code. My prep work, I do need the GA library again, and I'm also going to get ggplot2, which is a visualization library in R built around a notion called the grammar of graphics, which is a whole different talk. But I am going to put together a series of options, and I actually did pull these out of the game. And so I'm going to say each one of these has certain characteristics. You can improve the boxer's stamina, their speed, their power, and their defense. And each one of them also comes at a cost. So some items are more expensive than others. One of these items here has a cost of 3, and it provides you 1 stamina, 1 speed, 1 power. Or 3 power for 3 cost. Now this one here is a cost of 2, but it gives you 1, 1, 1. So obviously, whatever this particular element is, whichever item this is strictly superior to choosing this one. But then the question is, if I've got I have a cost of 8. It might be that I still want to choose both of these. So this is what we want to discern. My total cost is 8. I obviously cannot buy all of these things. Which combination of items is most efficient? And let me store my training balance and my training options. And efficiency is also going to matter on how valuable each of these skills are. And to that extent, I am going to need to build a fitness function. So this is like a cost function. This is telling me that the jogging machine has a cost of 3, but it gives me a lot of stamina and some speed. And so on. There are 19 total elements. Now, that means my chromosome is going to have 19 total genes because it's going to be, did I purchase this item or not? So in this case, if I run this, I bought the exercycle, the iron gum shield, jogging machine, and the protein diet. And so that was a total cost of 2, 5, 6, 8, total cost of 8. And I got 5 stamina, 3 speed, 1 power, 3 defense. And then the question is that good or bad? And the answer is, I don't know, because we don't have a way to compare that yet. So we need a fitness function. And my fitness function is, I'm going to do this. So every one of my stats will follow kind of a log form. So actually, I'm biasing toward a balanced boxer under the idea that if you just optimize strictly in one area, you can hit really hard, but you get tired fast and have a glass jaw. You're probably not going to be a great boxer. So each one of these has more of a curve than a straight line in terms of its impact on the fitness, the total fitness of a boxer, given my characteristics. I am doing some matrix multiplication of chromosome with my cost of training options because I also need to check here. What is my total cost of the options? Like, I could have a chromosome where I set everything to 1. Technically, that's valid. So I need to be able to control that in my fitness function and say, nope, you spent more than 8. That's an invalid result. And so I'm going to give you, a total fitness of 0. Otherwise, I'm going to give you something that's guaranteed to be above 0. So we're never going to benefit from exceeding our capabilities, exceeding our budget. And so, in other words, our fitness function has to control our budget. All right, let me see that sample chromosome, that boxer. So we're going to get a score of 9.04. Is 9.04 good or bad? I have no idea. We're going to have to find out. And then that gets to the question of, well, how do we figure it out? I mean, I could go with every possible combination of chromosomes here, and that would be 2 to the 19th possible chromosomes. That's a lot of a search space. And especially when we consider that many of these things are over the cost. So if I run this, I get exercycle, head guard, iron gum shield, jog machine, and protein diet. That is 2, 4, 5, 8, 10. My budget is only 8. I'm trying to spend 10. Not going to work so hot. So my fitness is a 0. So I know that I can limit this space by searching for only the subset of items that are below 8, or at or below 8 points. And I might get a little bit clever and say, well, I have to get exactly 8, because if I had under 8 and there was at least one item, knowing that these are integer increments, there's at least one item that has a cost of 1, then that would be strictly better than if I didn't get it and I just stuck with a total cost of 7. So I know that I'm going to be at 8. I know that I can't go above 8, and it doesn't make sense for me to go below 8. But even in so, that's still a pretty big space to search in. And this is where our genetic algorithm can come into play. In this case, our type is binary because we are solving a series of yes or no. Yes to the exercycle, no to the exercycle. Yes to the iron gum shield, no to it. My fitness function will be the evaluation. I'm going to have a population of 160 boxers in every generation. We're going to run 50 separate generations. And I'm telling them that the chromosome size is 19. I have 19 genes in there. And then I can set probabilities of crossover and mutation. I'm actually setting mutation pretty high in this case. Usually it's a lot lower than this, but I did want to show you just an idea of, well, what happens if I set mutation really high. And what we have, you can see a lot of means are not good, but if I look at the best score, because I'm not interested in what is the average of the population. I'm looking at what are the real winners in the population. And I start off, in the first couple of generations, I start off with 0. Nobody had a good result. But then we start pulling in, 966, 13.5, and we see gradual increases, 1409, 15, 15.35. It looks like it kind of capped out at about that point. So we probably could have stopped maybe somewhere around 60 generations, and we can see that it just never got better. So that seems like it was the best outcome. If I summarize my results, what I end up with is 160 population, 100 generations, 80% crossover, 20% mutation. My max score was 15.3. And if I plot what that looks like, we see those first few generations, my best score was a 0, but then we jumped and we jumped. So I just gave you the text version. This is the visual version of what we're seeing. And the mean and the median basically stay at 0 because a lot of the population is simply going over. They're spending too much money. But my model solution, my best outcome, given this information, would be iron gum shield, jump rope, karate, loose weights, punching bag, and running shoes. And you can see a whole bunch of low-cost items that tend to be pretty effective, like 3 defense. So, but that said, we can see that there are several of these where it's a cost of 1 and a skill value of 2. That seems to be how I'm able to maximize my outcome. And that gives me these values as my score, which may not have been where we would have focused early on. We might have focused on, well, I want fast and powerful because that's easier to work with. But given the way that I designed the fitness function, which we wouldn't have known, the machine wouldn't know, or the player of the game wouldn't know, it turns out that actually optimizing for a slightly different set of results turns out to be superior. That's an example of the knapsack problem as designed by someone who played a game of people hitting people, but letting us choose our best set of options. And this also works for things like, I want to maximize how many items can I fit into this truck, or what is the highest monetary value that I can fit into this truck. So I may have high-priced items that have either more space or less space required, and wanting to deal with this in a practical way. Speaking of high-priced items, my next example is going to be portfolio selection. So in this case, I want to maximize a portfolio of stocks while minimizing the risk associated with it. So let me walk you through that demo. So again, we're going to use GA for genetic algorithms. I will bring in QuantMod to get stock prices and time series to work with data over time. My data preparation, I'm going to pick a set of stocks. Some of these are, many of these are tech stocks. So, Apple, Google, Microsoft, and then a few other major players, Procter & Gamble, GE, etc. I'll use the QuantMod package in R to grab stock prices based on those symbols. And there we go. I grabbed data from 2017 through 2023 because, well, stock prices got a little weird in the last couple of years for some of these. And this ends up being a more interesting problem to solve than just the last year. But basically, I want to plot each of my portfolio items. And what I'm plotting is return on investment. So 0.05 is a 5% return on investment on a per month basis. And we see Apple here. We see all these different stocks, and some of them will bounce up, some of them will be jumping and dropping. And I'm not expecting you to be able to look at this and say, oh, here are the stocks that I think are going to work well. Instead, what we're looking at is, there's a lot of variance. And if I were to ask you, build me a portfolio in 2017, build me a portfolio that is going to give me the best returns in 2023. Or in 2023, build me a portfolio that we expect, given prior history, to get the best outcomes. Here's how we can do it. So our number of stocks, number of portfolio assets is the chromosome. We have this many genes. I have, 10 possible options. So what percentage of my portfolio is going to be Apple? What percentage will be Google? What percentage will be Microsoft? What percentage will be GE? And so on. The monthly return for each one of those stocks is going to be interesting. And the covariance matrix, how basically between covariance matrix and taking the square root of that, we're getting the volatility of these monthly returns. How volatile is that stock? Is it a consistent slow gainer, or is it something where 1 month it may jump 10% and the next it drops 20? And then I can build a volatility plot. So I plot the volatility versus the returns, and that shows me this. Looking at this plot, average monthly returns, this is higher is better. So this is saying 2.5% average monthly return. Hey, Apple's got the highest average monthly return. But this is the variance. Higher variance is worse. Ideally, I want to be in this corner right here where I've got good returns, low variance. I don't want to be in GE, which, that's basically been true for a while, because they've got high variance, low returns. So just looking at this intuitively, I could say, okay, well, I'm probably going to stack up on Microsoft. But then the question is, Apple has higher returns, but they also have higher volatility. Google has, it's a little bit lower than Microsoft and in terms of returns, but it's also lower than Apple in terms of volatility. Do I hedge a bit with Google stock? And this is the type of thing we want to try to understand. So we'll build out our portfolio as the combination of all of the stocks that we have, and our fitness function penalizes volatility. So we want to have less volatile, higher return stocks. So that is the formula in here. And building into our genetic algorithm, we're saying, okay, we've got, again, real type. So in other words, these are not binary. It's not zeros and ones. It's floating points. Our fitness function is this one right up here. At the lower end, we can have 0% of a stock. At the high end, we're allowed to have 100% of a stock. And our total summation is going to be 100%. So if I run through this, we can see results going over time. And if I summarize, in this case, actually, I should point out, I am trying to minimize the volatility here. So I'm trying to minimize this negative value, which multiply by -1 and maximize. It's the same thing. But my summary says that lower end I could have 0, upper end I could have 1, and the recommendation, stack heavy in Microsoft, a little bit of Apple, but not very much, and then a bit of WMT and PG. If I go back up to the chart, I didn't even talk about those too because they were way low on volatility, but they were also not great in terms of total returns. But what's nice is they were less volatile than Microsoft. And what that means is that these kind of stabilize my portfolio a bit so that I can play a little bit in the higher risk, higher return space while still getting pretty decent overall returns. So that may not have been a solution that a human would have come up with, but it turns out that this combination ends up maximizing our expected returns. And oops, I need to run this so that I can run that and say our variance here. You notice that the number did change slightly. Every time I run this, I may get slightly different results. And here's my bar chart with portfolio allocations, basically saying I'm going to weigh, obviously, Microsoft heavily and a bit of Apple and WMT and PG. But that was a way where we could take this dual problem of rate of return and volatility, alpha and beta, and how do we find the best solution for what we've got. Another example, I'm not going to show a demo here because we'll definitely go late on time, is the traveling salesman problem. So think about, I want to hit every single point in the minimum number of trips. In an ideal world, I do one loop and I hit everything. So what is the path that allows me to hit everything without repeats? And this is an example of going through every state in the union without a repeat. All right, takeaways for genetic algorithms. I will say solutions exist in multiple languages. I showed you R. There are solutions in Python. There are solutions in .NET and Java. .NET there's an older library. It's not so great anymore because it's abandoned, sadly. What genetic algorithms do is they're cutting through the search space. They're using crossover and mutation to possibly jump. So instead of gradual movements like a gradient descent, we may have drastic jumps where we're hopping over hills and possibly finding a global maximum even when everybody else is clustered around a local max. So they don't assume what is a good genotype, what is a good, which of these alleles is the right one. They just, by random choice and crossover, will try a variety of different options. Also interesting is that we don't have this idea of generational memory as such. We don't have the idea of this worked well and this worked well, and now we're going to generate a new result, a new iteration, and take those pieces of information. It's more of an emergent phenomenon where this worked well, which means it's going to show up in a larger percentage of the population, so it's more likely to propagate to that next generation. But there are no guarantees of it. I'll later on compare that to reinforcement learning. So I am going somewhere with it. Okay, genetic programming is my next bit. GP, John Koza, popularized this notion of genetic programming. I actually have a copy of this book on my bookcase back here. It is a big, thick book, and he had that's a series of, I think, 4 of those books. I only have the first one, but the notion of genetic programming is kind of interesting. It's a bit different from what we came up with genetic algorithms. So this is deriving a function, and I'm going to use a package called RGP. RGP was a genetic programming library for R. I have a note here that it was archived in 2018. It was actually a PhD project, and the person who created it eventually archived it. It's no longer available. It's no longer being updated, but I do have a copy of the library. So I installed it locally, and I'm going to say I have a set of functions. The way that genetic programming works is, think of, if you're familiar with the reverse Polish notation calculators, you may have solved a problem like that in a computer science course. It's kind of the same idea. I have a function. I can add, I can multiply, I can subtract, and I'm building a tree of functions and nodes. And so my leaf nodes would be, in this case, numbers, or maybe x. So I want to have x plus x, x times x, quantity x plus x times x minus x plus the quantity of x times x times x. I don't know. Whatever makes sense, whatever helps us solve the problem. So I've got plus, I've got addition, I've got multiplication, I've got subtraction. I don't have division. And I've got x. X is my only node, my only leaf node. And I'm going to build out a pseudo-random number generator, basically, and then give me a sequence from negative pi to positive pi, and it'll be by 0.1. So I'll go negative 3.1 to positive 3.1. My fitness function will be the root mean squared error of the function that I generate minus the sign over that range. So the idea here is, how close can you get to a sign function using just addition, multiplication, and subtraction? And we're going to call this genetic programming and send in my function set plus multiply, subtract. My input variables, you can have x. We've got one variable. My constants factory set, my fitness function over that range, and I'm going to let this run for up to 20 seconds. So that means I'm going to need to vamp for about 20 seconds while this is running. What it's doing is we're creating a series of generations of programs, essentially. Now, my program in this case is just a mathematical function. It's x plus x, or x times the quantity of x minus x. And it took me about 20 seconds. I generated 368 evolutionary steps and 18,000 evaluations of fitness. So who was best at this job? By the way, this was the last time I ran it. So we have constants like 0.4866 and minus whatever. If I run this, I get a completely different result. 0.66 times the quantity x plus 0.04 times 0.451. And my root mean squared error is 0.44. How does my best function do versus reality? This is my best function. Notice that in this case, it doesn't even try to match the curve. It's trying to match the relative direction, but it's not even attempting to be curved. Other times that I have run this, I have seen attempts at curves. So if I run this several more times, I may get different results. But let's suppose I had cosine. Now, go back to trigonometry. You can get 2 sine from cosine, but does the computer know that? Well, let's find out. So I'm going to run this function again. I'm going to run it for 7 total seconds. And that means I only have to vamp for up to 7 seconds, which if I already did it for 20, I can probably do it for 7. So as we can see here, 51,000 evaluations over 7 seconds. This is what I had before. Last time I ran this. Cosine of this quantity, x plus the quantity negative 0.58 minus the cosine of some constant. So let's run this again. We'll see what I get. Cosine of negative 1.57 plus x. Ooh, that actually looks pretty good, because basically we're shifting the curve by half of pi and adding x. Let's see how this works. See how it plays out. It turns out we nailed it. So it was able to resolve that this calculation is almost a perfect match for pi. For the sine of x over the range negative pi to pi. You'll notice my root mean squared error is 0.002. So very close. Not absolutely perfect, because this isn't exactly pi over 2, but it's pretty close. And there are some trigonometric functions that used to be available. Unfortunately, This is an old library, and so if I were to run this, I would not get a great solution. It's not going to look great. Basically, I'm only showing this to you because it was a fun example of what you could do with the library. I don't recommend using RGP ever. It was ended back in 2018. If you have a version of R that's 7 years old, it could work. But any recent version of R, absolutely not going to work very well. However, it is still it was still the best genetic programming library for R. And there's sadly not really a proper replacement in all genetic programming cases. So I showed you an idea of this is what it's doing. Let me talk about the concept of genetic programming, and then I'll show you some other similar examples. Genetic programming is itself an extension of what we got with genetic algorithms. So a genetic algorithm was a fixed chromosome. I have 18 genes. I have 21 genes. Genetic programs are artificial. There's no artificial limit to the size. There's no guarantee that you will have exactly 8 nodes in your program, 8 steps in the program. Instead, we're trying to solve this higher level problem until we have a solution. As far as comparisons go, it is very similar to a genetic algorithm. We still have populations of candidate solutions. We still have a fitness function that we need to build. We still have these new generations of candidate solutions. We still perform crossover and mutation. All of that stuff stays the same. The primary difference is the organism is the entire program. The chromosome, so it still has one chromosome, and that chromosome is the program that we create. So think of this as generating programs, and I'm having these programs compete to solve against my fitness function, and which program does the best. So very simple program. My fitness function is 56 minus x, that quantity, 56 minus x squared. And my candidate solution. So maybe I can do multiplication, addition, and subtraction. So I have 8 times 7. Well, 8 times 7 is 56. 56 minus 56 squared is 0. Cool. I've nailed it. I've gotten my answer. And this would be a good program. In reality, you're more likely to see programs that look like this. Well, 8 times 8, and then that quantity minus the quantity 4 plus 4. And if you do the math in your head, you realize that still gets you to 56. But you have more steps involved. You have more generation. And our crossover is we would take a subtree and basically swap subtrees. Our mutation is we might change a component. Instead of a plus, maybe we make that an X. So we still have those ideas of crossover and mutation, but they're slightly different. We're now dealing with trees instead of arrays. Genetic programs, I showed you an example of it deriving a mathematical relationship. Well, we can also do a bit more with genetic programs as well. Let's take a quick peek. I am actually swapping to a different library. This one is GramEvol. Technically, this is something slightly different. It's called grammatical evolution. So it's not truly genetic programming. However, it is a library that's still supported in R. So what is our problem? My problem is I've got some data. I've got an X and I've got a Y. And we're going to look at that series. And what I want to do is I would like to find some mathematical function that most closely adheres to this curve. So if I drew it a little bit better, I would have all of these dots would be exact center of my curve. And I want to derive what is that function. So how do we do that? Well, in GramEvol, we have a few different function ideas. We have basically we're building out a set of rules, and I can have sine, cosine, log, and square root as my function, as my functors. I can have addition, subtraction, and multiplication as operations, and I'm allowed to have an operation with 2 expressions, or a function of an expression, or just a variable. So my variable is x. And that is my grammar. Those are my possible viable options. So if you think about the tree, I can have the sign of some expression. I can have, and by the way, this can be nested. So expression is a little bit recursive in here. But I can have the sign of 8 plus 8. And then I need a fitness function. So my fitness function, I'm going to point that if I get not a number, like if I try to take the log of a negative value or the square root of a negative value, that's not going to work. So if I get not a number, you're infinity. You are so far off, you're never going to be a solution. Otherwise, give me the mean of the log of 1 plus the absolute value of y, which is my actual value, y, minus result. So what result's going to give me is an equal number of values. I'm going to get basically 7 data points, and I'm going to compare each one of those data points to what we actually have in y. So let's generate that, and we're going to build a solution. Now here, my termination cost will be 0.1, which means that it'll stop if I ever find a cost that's within 0.1 of the correct answer. I'll go 2,500 iterations, and I'm allowed to go 8 levels deep. So my tree can go up to 8 levels deep. These are all controllable functional values, parameters for input. And unfortunately, this is going to take a little while. So while it's running, let me show you what an older run through looked like. If I plot X and Y and then I have my best output, I ended up with a function that looked like this. So this is not perfect, obviously. You can see that it certainly falls off because it's kind of expecting, it looks like it's a quadratic function that's some type of square result. And this is the actual expression. And you can see this is not a simplified expression. This is not how you or I would write this. We would say, why do I have x plus x plus x? I would say like 3x. And try to minimize the number of overlapping parentheses and try to simplify this formula down to the minimum understandable bit. That's parsimony. And this goes back to the point that genetic and evolutionary algorithms are not parsimonious by nature. There is no guarantee of parsimony. And let's see what this run through looks like. Oh, we can see there's a little bit of a kink here at 5. So it does a better job on 6, but does a little worse on 5 and 7. And the formula for here is this, which, again, have fun. We'll have some fun trying to sort that out. But at least we can see it generated a formula for us. It generated an answer that kind of gets us to the real answer. And what is the real answer? I actually don't know. I just picked these numbers arbitrarily. It doesn't follow a classical standard formula as far as I'm aware. This is empirical. But we could estimate something that gets us in that general direction. So we can derive nonlinear functional results like a regression model. And by the way, if you are regressing, as a quick note, genetic programs tend to overtrain on current data. So they're better for identifying a formula than doing a true regression. But I'm going to show you a regression regardless. And I'm going to use DBA salaries because, so far I haven't really talked data at all. So one use, genetic programming, let's build a regression tree. Technically, again, this will not be truly GP. This will be evolutionary trees. But who's going to stop me? So the question is, all right, you're a DBA or some other data platform professional. How much money should you make relative to your peers? Or rather, based on what your peers are making. So let's look at this. DBA salaries. This is another example using something called an evolutionary tree. EV tree. EV tree is technically still supported, but for whatever reason, CRAN thinks that this is more than I do. CRAN thinks that this only should be installed on old versions of R. So once again, I'm installing this from my repo, my GitHub repo here. But this one is still on CRAN. It is still technically an active project. It hasn't been updated in a while, though. I'm also getting the tidyverse and read Excel to be able to read an Excel file. This particular data set is Brent Ozar's DBA salary survey. He's been sending it out since 2017. And actually, to give you an idea of how old this talk is, the original version of this was the first salary survey from 2017. And I decided I'm going to update it to use the 2024 data, which includes all the responses going back from 2017 up to today. And so that is roughly 12,980 responses. And I'm going to read the Excel file, and I'm going to say, start in column Charlie 4, go to Alpha Delta 12,983. And by the way, make your data type guesses based on the first 13,000 rows, because, in other words, don't guess, just pull all the data in, because I don't want data types to be wrong later on. So if I take a quick peek at this data, we've got a lot of different things. The thing that I'm caring about the most is the salary in US dollars. And so people put in their annual salary in US dollars, the country in which they live, their postal codes, what is their primary database. So Microsoft SQL Server will dominate this because most of Brent's audience is SQL Server people. Years with the database, and a bunch of other input factors. Now, some of these input factors, Brent did not ask in early years. So like number of employees overall, he did not ask in the first couple of years of the survey, which will affect our results and actually makes me want to just drop those questions because it'll make it easier that way. Now, let me take a peek at that salary data. Again, we can see that there are 28 columns. If I scroll through here, some of these columns are kind of wide, but you get an idea of job titles, whether they manage people, how long you've had the job, et cetera, et cetera. So pretty good survey. I'm going to do a bit of cleanup. I am going to take salary data only for the United States. There's a huge variance in terms of salary. Somebody in the US, we would expect all things equal to be making more money than someone in Botswana, just because purchasing power parity differences. So I don't want, if I'm talking about people in the US, I'm going to focus on US prices. If I were talking to a Canadian audience, and if I have enough data points from Canada, I would either filter country equals Canada or take US and multiply by 3/4. But I'm also going to focus, you're a SQL Server DBA or SQL Server data professional. That's your primary database. Again, most of Brent's audience is SQL Server. So if I were focusing on Postgres or Oracle or MySQL, I'm going to have many fewer in data points. Employment status. I'm only concerned about people who are full-time. That could be you're a full-time employee, you're an FTE, or you're doing full-time at a consulting or contracting company. There are also part-time. There are people who own a company. There are people who are unemployed. Salary per year, less than or equal to $500,000. There are some data points where people are making $1 million a year as a DBA. And if you know one of those jobs, I would appreciate a hookup. Years with the database. Some people put the year that they started working with the database. So there would be cases like 2008, 2009, 2010. And I would say if you've been working at a particular database for 2,000 plus years, that might explain why you're making $500,000. So just some essential data quality cleanup. Wall Street and not worth the money. Yeah, no, that's a fair point. And then we're selecting. What are we selecting? This is my salary. This is the thing that I want to understand, the variable, my label variable. And then I have my inputs. I believe that how long you've been working with SQL Server will matter. How long you've had a particular type of job will matter. Your education level, your job title, which could be like a DBA, a data scientist, a developer, application developer, etc. Your employment sector, government, federal government, state government, or private sector. And do you manage staff? I would expect those to be factors in whether or not, or what your salary would look like. So that's my set of data and variables. And so I'm left with 6 relevant inputs leading to an output. With that, what I want to do is try to discern what factors impact salary the most. So I can build a regression tree using the EV tree library, and I'm going to try to solve for salary based on all of these other inputs. What this will do is it will generate a series of regression trees. It'll use the same evolutionary concepts we talked about of crossover and mutation and build a series of trees, compete, swap around, and generate some results that look a little bit, well, I was hoping that it would be done so I could say look a little bit like this, but it'll take a moment to finish up. What it will give us is one answer. We may have had a large number of trees, but we're leaning toward one answer, and that is, well, let's say if your number of years with the database is less than 7, that might be one of our branches. So while it's going on, we're building out a tree. Each tree will have 2 possible branches. We can have, at most, 6 levels of depth. So, I can only go so far with this. But then the end result is that I'm going to get some range band. It's going to say between this dollar and this dollar amount if you fit these characteristics. And then maybe if you fit some other characteristics, then here maybe this is you're actually going to be lower because you're not a manager or you haven't worked as long in that field or whatever, or you're an app developer instead of a data scientist, so the job title and the roles and responsibilities will be a bit different. Now this is still going, so if there are any questions, this might be a good time for a question or for me to take a drink. Well, while this is going, this turns out to be the one where I don't have a pre-created example. So naturally, it's the slowest one of them all. While it's going on, I do see a couple of people typing in, what is the CPU of the host? I've got a pretty fancy Ryzen 7950. So this is my desktop computer, but pretty fancy one. Let's check out what it's doing. It's actually not killing my machine very much, but it's probably also not taking a whole bunch of cores. This is also not a particularly optimized library in terms of performance, meaning I wouldn't throw a large amount of data at it. You could write, R optimize that. Depends on the library. And we have our results, and this, wow, look at that. That doesn't look good at all. That doesn't look fancy at all.
I was about to ask if the result would be human readable.
Is the result? Well, fortunately, if I just look at the object itself, this is a lot more human readable, I think.
Okay, cool.
Because we have our root, and we say, okay, well, if you've, debatable. Okay, fair enough. You spent less than 8 years with this database. Oh, you spent less than 5 years with this database. Oh, you've had less than 3 years at that job. All right, we expect that your salary will be about $70,000. But if you've had more than at least 3 years, you got a pay bump. Now, if instead of 5 years you're at 5 to 8, and if you're an architect or a database specialist or one of these things, $107,000. But if you're an analyst or an analytics consultant or a data scientist or whatever, $91K. Oh, that's kind of interesting. So we can dig through this, and there's a lot more depth here than what I normally get in the result. But what we can find is I now have the characteristics that could drive what a salary could look like for a person. So I can build a predictor, and I could say, give me the EV prediction and predict based off of that. Now, my comparison, I'm going to compare it to linear regression. Linear regression is, my standby. if you can't beat linear regression, then what are we doing here? And that's because linear regression, more often than not, actually works really well. So in this case, I've generated a regression model. I'm going to generate predictions off of that. And we are going to use root mean squared error. So root mean squared error of my EV is about 27K. So this is in US dollars. Basically, on average, I'm off by about 27 grand. For the linear regression, I'm off by about 27 grand. Essentially, it's about the same quality as the linear regression in this scenario. What that's telling me is that there probably aren't a lot of quadratic inputs. There aren't a lot of things that scale non-linearly. And so linear regression actually probably is a somewhat reasonable solution, knowing that, well, my error term is still pretty high. Also of note is this is a data set that constitutes 2017 through 2023 data. And what that's going to mean is, well, we've had inflation over the past few years, which means that salary changes have happened. We did have that 2020 thing happen. So there can be higher variance in salary expectations as a result of all of this. Nonetheless, we're going to carry on. We were able to generate a result. In other circumstances, we can end up with actually a really good result. I have a separate talk that's on optimizing backup performance using data science techniques, where I use evolutionary trees to help determine what is the best set of backup settings, like number of buffers and max transfer size and block size and file count, to minimize the amount of time that it takes to take a backup in SQL Server. And the evolutionary tree actually does a really good job of that. And it helps you explain quickly, here are the characteristics for your particular environment. So I can drop a link to that in chat in case you're interested. It is kind of a hybrid DBA / data scientist talk, but there you go. That's in there if you want it. But going back to this, my test cases, I've got a few different scenarios. Years with the database. Basically, I have brand new person, someone who's got 5 years, 8 years, 11, 16, and 18. Years with a particular type of job. And I kind of based this on me. So introduction to the industry, 5 years as technically I was an app dev at that point. But I'm going to count myself as DBA in here. 8 years, and then became a manager, 5 years as a manager, and then now I'm a data scientist. So we have our different inputs. Sometimes those state government, private business, and whether or not I was a manager, et cetera, et cetera. If I run through this, here are my values. Notice that I don't have a salary because I want to figure out, well, what do we think the salary would be for each one of those people in those circumstances? And our brand new person in the field, 70K, 5 years working at a state agency, 91K, 8 years working as a development DBA in private business, 107K, becoming a manager, pretty big bump, 5 years as a manager. And it turns out data scientists, according to this, had effectively no salary difference. For my linear regression, you'll notice that the differences for an introductory person, that's a pretty big difference. But 5 years of experience as a state employee here versus here, they are seriously underweighing the state employee. I will note that this was closer to the real number, as I recall, but it's been a minute. But you can see, as we get a little bit higher, even here, there's still some differences. There's still some disagreement in the exact nature of what these two tell us. But what is interesting to us is that I would say both of these can be wrong in both directions. So kind of interesting to see where they disagree and having a little bit in my head of what the real values were, but I'm not going to spend a lot of time talking about that. It's it makes sense a little bit. Okay, regression trees on the whole, in this scenario, were not better than linear regression. In other scenarios, they can be. The attributes, you can argue about whether it's more understandable to a layman based on a tree with that bunch of if-else statements, or if I show you the block in R where we summarize a model. As a person who has read these things quite a few times, I can get a lot of information out of it. As a non-technical layman, this is kind of scary. The takeaways. Genetic programming. Finding arbitrary length solutions to problems. The best library that I've seen for this that is still around. Actually, that's two separate sentences. The best library that I've seen for this is ECJ. It is a Java library. It is still around. This is hosted by George Mason University in Virginia and is an evolutionary computation toolkit. To give you an idea, I actually wrote my master's thesis building a genetic program in Java back in 2007 using this library. So it's still around. It's not incredibly active, but it still works, which is better than like RGP, which sadly is no longer working. Other libraries in this space tend to be more of symbolic regression, like the Gram-Eval that I showed. Or in Python, there's GP-Learn, which is kind of scikit-learn flavored, but is for one aspect of genetic programming. The broad-based genetic programming concept is much more interesting, I think, than what we get just in terms of symbolic regression, but there are very few of those libraries outside of ECJ. All right, couple minutes, alternatives to evolution. Reinforcement learning. You may be familiar with the idea. The idea of reinforcement learning is we have a single agent that is trying to perform an action. That agent will get a reward based on how it did. Then it'll try something new, and it'll compare, what does this reward look like versus my last reward? And we can track these different reward paths. Well, if I take step A, then B, then C, I get a reward of 20. If I take A, then D, then F, I get a reward of 35. Okay, well, ADF seems to make more sense. Well, what if I do ADG? Oh, that's only 26. All right, well, ADF, and then I'll keep going. So this is kind of the idea. We're moving forward, backing into and applying, well, this A path tends to give me some high results. This B path doesn't give me very high results at all. As I explained it that way, I think you can see there's some similarity to evolutionary algorithms. We're still maximizing an expected, we're trying to maximize, in one case, an expected sum versus, in the other case, the fitness of a whole population. So that's a difference. In reinforcement learning, we have one agent. In evolutionary algorithms, we have a population with many agents. All of those agents are independent. Our reinforcement learning, there is actually more mathematical grounding. This is, in many cases, it's kind of built off of Markov chains, whereas genetic algorithms are actually more heuristics. We're taking advantage of the fact that by swapping things around, by Frankensteining our population, we can actually end up with some good results. Reinforcement learning focuses on that intra-life learning, so we have that experience replay, which is what I was talking about with, if I go down this path, I tend to have better outcomes than if I go down this other path. Whereas genetic algorithms and other evolutionary techniques are inter-life. We don't improve the quality of one chromosome within its own life. Instead, we carry on to the next generation what were the most effective chromosomes from the prior generation, plus a bit of swapping and mutating. But hey, you can actually have both. And there's a good paper by a set of authors around genetic algorithms combined with deep reinforcement learning. So neural networks, reinforcement learning for parent selection. In other words, think of your the way that I showed genetic algorithms and how you choose parents, where we just sum up the results and you throw darts at a board and pick based on likelihood that, oh, it's going to be this this because it had a higher fitness. We could use reinforcement learning to narrow down the sets of parents that we're choosing more quickly than fate. So we could get faster conversions on more complicated problems. So it's a nice way of trying to combine two similar but a little bit different techniques. When it comes to neural networks, I did mention early on, neural networks, these have dominated machine learning for 12 plus years. 2012 is basically when I would consider neural networks took over machine learning, for better or for worse. Now, even so, neural networks solve a particular type of problem really well. They are extremely good at approximating functions with continuous data. Image classification. If I show you a whole bunch of images, I give you 1 million images, and I say, these are cats, these are dogs. Tell me if this image is a cat or a dog. Neural network is fantastic at that. Specifically, certain types of neural networks are really good at it, like convolutional neural networks tend to be really good at that. When handling natural language, there are other types of neural networks, generative adversarial networks, or things using long short-term memory or transformers that are really well designed for the type of problem. A genetic algorithm isn't going to solve those types of things necessarily as well, but it is actually better for broad-based search, complicated search problems. And one area where we can see the combination of them is using genetic algorithms to help derive our actions, our set of actions that a neural network can take. This is a YouTube video from, it's about 9 years old at this point, but I'll drop a link to it in chat here. It's a really neat bit of code that a person wrote, and the video was, it's called Mar.io, and uses a neural network to play Super Mario World, the first level, and it uses a genetic algorithm to basically figure out what is the fitness of a particular playthrough, a particular round. So we're using genetic algorithms to give us an answer for the neural network of, did you play this round well? Did you solve this level in a way that I want you to solve it? And we may include things like, how many coins did you get? How quickly did you complete it, etc. Takeaways there. Genetic algorithms, they are different from neural networks. They are different from reinforcement learning. There is some interplay where we can see them come together and work together. Genetic algorithms and evolutionary programming are good for specific use cases where I have an extremely broad search area, and I don't necessarily know how I get my answer, but I do know what a good answer looks like. In other words, solving hill climbing problems. It does a pretty good job of that. Now, if you want to grab these slides, if you want to grab the demos, if you would like to get links to additional resources, that is all at csmore.info/on/GIA, Genetics in Action. And if you want to reach out to me afterwards, you are absolutely welcome to. I will put in my email address. I'm also going to drop in my handle on X. And with that, I want to say thank you so much.